Hello everybody. Thanks for coming out. We'll try to make this worth your while.
Are you related to Leo?
And no, well, we talked about that, but neither of us will admit to it if we are. We don't want to go that far back and check the roots, but apparently all Vaillancourts are related in this country, so somewhere along the line. Let's give this a second to warm up a little bit. So we talk about combined heat and power, and like Russell's, I've been looking at following this technology for quite a long time. I remember looking at fuel cells when they were in the development stages, over a decade ago. And fuel cells, although they've come a long ways, they're still priced way out of the market. They can't build them cost effectively, and so the next best thing is going to be combined in heat and power using other technologies. So we'll have a chance to answer some questions after the presentation. If you don't mind, I'll try to go through it and explain everything as best as I can. We're starting to see there's actually quite a few different manufacturers around right now producing combined heat and power systems, and you're going to start seeing them at trade shows. You see them mostly in the U.S. currently, and the New England states is where there seems to be a real uptake on this type of product, and we're starting to slowly see some market penetration into Canada. So we're going to talk specifically about micro-CHPs as opposed to large-scale CHPs. CHPs have been around for a long time, industrially, but they're too big to be used in the smaller applications where we could really benefit from that technology. And also, the larger the scale of the equipment, typically they're not able to achieve the efficiency ratings that we're able to on the smaller equipment. So it's anticipated that this technology will evolve to a point where you're going to start seeing it in homes on a much smaller scale. So when I talk about CHPs, I'm talking about combined heat and power. An MCHP is merely a smaller version of that. It's called a micro-CHP, or micro-combined heat and power. It's 50 kilowatts or less capacity would be considered a micro-CHP. So it's distributed power generation, meaning that the electric power generation is close to the point of end use. So we're going to start seeing, over the past few years, everybody's called it combined heat and power, or CHP units, and you're going to start seeing that changing to distributed generation is going to be the new terminology for this technology. Cogeneration simply means it's simultaneous production of heat and power. And it's usually installed where there's a fuel source, such as natural gas, which is abundant in our area. These units can run on propane or on biogas, etc. And they work really well. They're a viable alternative where you have not only an electrical demand but also a thermal demand. And that's a real important point. If you don't have both, then don't even worry about, don't even consider it a micro-CHP. I can buy power probably cheaper than what I can generate it if I was just looking at producing electricity. But if I can get two sources of energy out of one supply source, now I'm getting some efficiency. So kind of in a nutshell, it's really simple technology. Most CHPs in the market are using internal combustion engines. There's a few that are using other technologies. Some are using, the Stirling or external combustion engine. But most of them are using internal combustion engines because they were able to get high efficiencies out of these engines. They were able to build them so that they can get some real longevity out of them. But basically all it is here we're showing there's an engine running on natural gas, and there's a generator that's typically directly coupled to the engine, and this would be an AC generator, and there'd be a heat exchanger in there. So the unit itself is not very complex, right? You got motor, heat exchanger, and you have to cool that engine like you do any other vehicle. So what they do is they have this heat exchanger in there, and the water that circulates through the jacket of the engine to cool the engine. They're going to try and extract as much heat as possible. So they're going to extract heat off the engine itself. They'll extract heat off of the oil, so they'll have an oil cooler on there. They'll extract heat around the generator itself because it's producing some heat. And then a big part of it is going to be the actual exhaust. So there's the exhaust system, or the muffler, if you like, is actually an energy recuperator. So there's actually coils and water circulating through that as well. So they're able to extract a huge amount of energy in the form of heat, and then that would get plumbed, and with a small circulator could go into a storage tank. And then from that point, that storage tank now becomes your distribution center for all of your various loads within the building. So while all of this is happening, the engine's running, you're producing some hot water. At the same time, you're producing electricity because it's turning that generator. So the power is tied back to the panel. If this was, could be in a home or it could be in a commercial building. It's a very simple tie back into the electrical panel, and as long as there's a demand in the building, it's going to want to use that power within the building before it takes electricity off of the grid. Right? It's going to use it, whatever power you generate, it's going to try and use that up. If you're producing excess power, it's going to feed back into the grid. So now with the smart meters, they're bidirectional meters, and if you actually look at a smart meter, you'll see that you have two readings. First one is being power being consumed, and that's cumulative from the time that they put the meter in. It never dials back, right? It's always moving forward. And then if you wait long enough, you'll see another little window that's going to come up, and it's going to show you power that you're giving up to the grid. It's going back the other direction. So an example layout, very simple. You've got your CHP, there's a heat exchanger in that CHP, and you can see here that there's a storage tank. In this case here, this particular unit, I've installed a few of these units, or sold and commissioned a few of them. It's 4.7 kilowatt combined heat and power unit, and it's putting out on the thermal side roughly 45,000 BTUs. But it'll produce water up to about 167 degrees Fahrenheit. Could actually go a little bit higher, but we try to program in that set point, 167 degrees Fahrenheit. And you can see all this is between the unit and this tank. This is a 250-gallon storage tank, insulated of course. Small circulator, and that's 1-inch copper pipe between the two. And then there's a mixing valve there. And the only purpose for that mixing valve is that when that engine starts, if you're going to start with cold water temperature, it's to bypass some of the water to get that engine up to temperature fairly rapidly. And then the valve will start to open up and start exchanging water to that tank. So here they're showing 3 sensors in the tank, one at the top, one in the middle, one at the bottom. There's software and electronics in the unit itself where you can monitor and know exactly what's going on in that tank at any given time. One of the interesting things that you might see here is that the hot water is actually going into the top of the tank. I know with geothermal applications in the past, they always used to introduce the hot water at the bottom of the tank, allowing thermal migration within the tank. Here they're actually top loading the tank so that you always have the hottest water available for point of use. And it will stratify downwards. So at some point, these temperatures are all going to be close to being equal. So the integration, or this portion of the system, and really that's By doing it this way, what you've done is you've mechanically decoupled the CHP from the entire system of the house. All that CHP cares about is the water in that tank and what temperature it's at. So it makes everything downstream of that really simple. Now you can do whatever you want downstream. You can have various flow rates, it doesn't matter. It doesn't affect the CHP. In terms of troubleshooting, it's a lot easier as well.
Why do you troubleshoot?
I don't know, I haven't had to yet. It's like the Maytag. So here you can see CHP, the tank, and then you have your various loads downstream of that tank. You can have various flow rates. You could be feeding some radiant floor heating if you want it. You're going to have to mix it down because your tank temperature is going to be a lot hotter than what you want to put into those floors. But you could also be doing in an indirect tank of some type, whether it's a coil or a separate heat exchanger, fan coil units. You've got an abundance of energy there in the form of hot water. You can do whatever you want with it. In 2 installations that we've supplied, they're heating not only radiant floor and domestic, they're doing domestic water, they're also heating an outdoor pool, and they're heating a hot tub as well. So, and that's where, that's a perfect application in a residential system where you have an annual thermal load. You've got a load all summer long, right? Now you can keep this unit running. The more this unit runs, the more money it's going to save. So, you can parallel the systems as well. Here you can see, again, it's simply 2 CHPs. And you can see there's a complementary boiler on the system. Always a good idea to have a backup source on that system. There are times where the CHPs, even though you have a lot of thermal mass, you're still only putting out 80,000 BTUs. The difference here is you could be doing this 24 hours a day, 7 days a week. But there are times where the peak load is going to exceed the capacity of the heat pumps, and you could have your boiler kick in to pick up that difference in temperature. So you set the design parameters for that. So as far as interfaces go on these systems, really what we have is we have an appliance. We're going to have to do some venting on it. These are actually a condensing unit, so they can condense. You're running an internal combustion engine that condenses, or they can condense. And so the vent pipe typically is going to be a CPVC, or it could be, like a sorry, there's a couple of brands of polyethylene pipe, Polypro, or any of the other brands that are out there. So venting is...
Boiler application, sorry, is it a boiler application, or is it something down around condensing gas furnace?
I'm sorry?
Well, I just think about the piping, it's 636 shed 80, or?
It's got to be 636 CPVC, so a little higher discharge temperature, right? But it can condense, and that's why you can see there's a trap there on the bottom. So as far as integrating in the system, so you got your venting, you've got your gas supply coming in, and then you've got your water side going out to your storage tank, and then the only other interface will be the electrical interface between the unit and the panel. This being a 4.7 kilowatt unit, that interface is simply a 10-2 wire running to a 30 amp breaker in the panel through an isolation transformer. So this gives you a bit of an idea of that electrical interconnection here. So the isolation transformer is there as a safety, and and we're putting power back onto a 30 amp circuit. It's going to feed back into the house. These systems are grid dependent, and this is one of the things that I get asked all the time. Well, does that mean I can run, when we get a power outage, can I run this unit? And the answer is no. It's not there as a backup generator. It's there to produce some energy and save you some money. So it is grid dependent. And to meet all of the CSA requirements, it has to drop out within, I can't remember exactly the number of milliseconds, but if the power drops out, this unit has to drop out very, very rapidly. And that's to protect the linesmen down there, right? So that we're not feeding power back and they're working out the power lines and not expecting that power there, and all of a sudden they're getting electrocuted. So the interface is very, very simple. A typical installation for, say, a single unit, and I've seen it now on a few occasions, once the equipment is on site, and that's a big part of the challenge because you got a unit that weighs almost 1,000 pounds on its own. Once the equipment's on site, two guys can easily retrofit one of these guys in a day. You know, it's that, because there's really nothing to it. It's a couple of copper lines, you got your gas line and your power and your venting. So it's a pretty simple installation from that perspective. The units, you'll see a rating plate on them, same much as you would on any other gas appliance. So it'll give you, apologize for the clarity, it's not very good, but it gives you the fuel type, what the input firing rate is, what the output power would be, and the range of operation. So I'm just going to move forward here. So some of the manufacturers that are out there, and as I mentioned earlier, most of them are using internal combustion engines. And so there's DOX, which is in Germany, uses an IC engine, or internal combustion engine, the IC engine. And that's the parent company for that is Baxi Group. Baxi is kind of interesting because they have two different CHPs. They use internal combustion in some units, and they also use external combustion engines in some of their smaller units as well. Genelite out of Japan, which is Yanmar, is probably one of the bigger names out here. Most people that have looked into CHPs know about Yanmar or read about Yanmar. The ECCO power unit, which is Power Plus Technology and Marathon Engines. So that's actually two companies that did a joint venture, if you like, one based in the USA, in Wisconsin, and the other one based in Germany, and it's the Vaillancourt boiler manufacturer, which are considered to be high-end, high-end boilers. So Vaillancourt builds the cabinet, and they build all the electronics for the engine, and Marathon Engines, of course, builds the engine itself. So originally they were just building the engine for Vaillancourt, shipping them over to Europe. And then they came into an agreement and started manufacturing these units in the U.S. The Whisper Gen uses a Stirling engine and EcoWheel free watt uses an internal combustion engine, and that's out of Japan, and that's made by Honda. So, and they, Honda with their EcoWheel or their MICRO-CHPs now have exceeded 100,000 units. Some of the other ones are relatively small numbers, compared to other technologies for sure. 8,000 for DOX. The ECCO power unit is 4,000 plus units, mostly in Germany. However, we're starting to see some market penetration in the U.S. and in Canada now. So I know of units in this province. Alberta has some units, Saskatchewan has units, then I think it goes to Nova Scotia after that. So the very small number of units in Canada, but really they've only started marketing the product a couple of years ago. They actually, when they built the American version of this, they had it in the field, and they were testing it. They had a number of units out there. They were testing them for 5 years before they said they were ready for market penetration. To give you an idea of the scale, to have this many manufacturers and the dollars that they have to invest in these technologies, they've got to have a pretty strong belief that this is going to be moving forward. ECCO Power itself, or Marathon Engines, has $75 million invested in one product, just to give you an idea. So the internal combustion engines are developed for long life. Recent developments include improved emissions ratings and longer service life, higher electrical efficiencies in the 20 to 30%, compared to the Stirling engines at 10 to 15%. And this is, yeah, we're just talking on the electrical side. The Stirling engines don't perform quite as well as the internal combustion engines in terms of generating electricity, because they use a linear alternator as opposed to you know, an AC generator that would be coupled. So there's some efficiency loss there, but they are approaching 17%, I think, with actually Navian has one. It's not available in North America yet, but they're about 17% using a Stirling engine. But the IC engines are seeing efficiencies typically around 25% on the electrical side. So internal combustion engines are used by most manufacturers. Marathon, Yanmar, Honda, Freewatt, Baxi, and others use internal combustion engines as the prime mover in their CHPs on the market. So again, when we talk about the engine, we always refer to them as, you know, somebody will ask you, well, what's the prime mover in your product? And they're referring to the engine, what kind of motor you have in it. So if we look at cogen system, we have to look at combined efficiency. So when we look at the you know, power generating efficiency, this is on one product. Their power generating efficiency is 25%, heat recovery is 68%, and waste heat is 7%. So the combined efficiency or overall efficiency is considered to be 93%. Where you're going to be able to use, you know, that 93% of the total energy that's being produced within the building. So the internal combustion engine itself, really simple on a 4.7 kW unit. This would be a 16.6 cubic inch single cylinder engine that will vary, but can run up to about 3,600 RPM. And they can run 4,000 hours continuous at the top RPM. So that's pretty amazing when you think about it. You know, at that RPM, it'd be like putting 500,000 miles at 100 miles an hour before you have to do an oil change. So they've built these engines pretty tough. There's actually 11 liters of synthetic oil that's used in these engines. So it's a big sump on them. And then as far as maintenance goes, it's pretty simple. Spark plug, one spark plug to change, you got a plug wire. Of course the oil filter, air filter, and that'll get you 6 months of continuous operation. So with Marathon, it's kind of an interesting history. It was actually Briggs and Stratton that developed this motor originally, and it was back in the 80s, and it was for York International, and they used them in a heat pump they had. It was called the triathlon heat pump. And then you know, over the years, York decided to they abandon that product, but the engine still had some value in it. So Marathon bought it, improved on it, and because of its long life capability, and we started to use them in CHPs. So just looking at the engine data, water-cooled, single-cylinder, 4-stroke piston, combustion engine designed for long running time, 16.6 cubic inch, speed range 1,200 to 3,600 RPM, and the factory setting is usually below the max, so 3,400. And the coolant temperature 167 to 176 degrees Fahrenheit, short term up to 194. So maintenance interval every 4,000 hours. And some of the other manufacturers now, like Yanmar, I think they're going 8,000 hours now between oil changes on their engines. And I know that these guys are also looking at changing their intervals as well. The generator would be, in this case, a brushless permanent magnet generator, directly flanged to the engine with a water cooling system. Has 3-phase inverter with integrated safety monitoring, microprocessor control, single-phase output for North America. you look at some of the other products like Baxi, they have wall hung units, so they're the size of a small boiler. And in this particular model, they use an external combustion engine. The same with Navion with their hydrogen model, which we're hoping that will make a market penetration here soon. So they're nice and compact. And for external combustion engines, it's a much simpler engine design. Probably some advantages in terms of longevity, but they work differently than any other internal combustion engine that we're used to, where they use helium gas. And so they use the burner to heat the helium gas, which will expand and push the piston down along a linear generator or alternator. And then as the gas cools with the water circulating, then it'll compress and push the piston back up. So it's pretty simple engine design. They haven't quite got the efficiency out of it yet. So the whole concept with these units, as I mentioned earlier, is you want to be able to have a good annual thermal load and a good electrical load. You need both to make this worthwhile. And there's a ton of applications for it. Pools are a great example of that. And anywhere where you need a lot of a large domestic water load would be a good example of that. So as long as you have a thermal load there, you can produce electricity. That electricity could be used to offset some of the costs on the other building loads, your ventilation systems, your hallway pressurization, your lighting, your external lighting, all of these things. So they've been used in car wash applications, laundry facilities. They need both a lot of heat and power. And the technology is totally scalable. So one thing with MICRO-CHPs is that they're typically designed to work together, so you can put them in parallel. And when you look at the performance is linear in that the relationship with the amount of fuel that it's going to consume is always going to follow that linear scale, where it's going to be the same at the low end or at the high end range. So if I look at how much gas I've consumed, I could pretty much calculate how much electricity I've consumed, or vice versa. On a larger scale project, where storage might be an issue in a mechanical space, there's always the option to put an underground thermal storage tank as well. So the key with, if you have a lot of storage capacity, you can keep that unit running all the time. So even during your low demand periods, keep the unit running, keep storing the energy for when you need it. And while you're doing that, you're producing electricity. The other nice thing with storage is that you can integrate other sources of energy, and once you have a storage bank or storage capacity, right? If you wanted to integrate solar into that system, you could. If you wanted to integrate any other type of energy, thermal energy, you could store it in that same tank. So when you look at the cost comparison for electricity generation costs with and without cogeneration, if I was just looking on the electrical side, if I was running that engine just to produce electricity, depending on the cost of my fuel, the blue line would be the natural gas, and the red line being, or sorry, the red line is natural gas, the blue line is actually propane. So if I was at $1 a therm, or sorry, what was that? Bear with me for 1 second here. Yeah, cost per therm. So $1 a therm, so a therm being 100,000 BTUs. And if I was only using that engine to produce electricity, my cost to produce electricity would be somewhere around the 12 to 13 cents per kilowatt hour, which is the same as what I could buy it for. I might even be able to get a little bit cheaper from utility. But as soon as I can use the heat, now I've got combined efficiency. Now my electrical cost is somewhere around between 2 and 3 cents per kilowatt hour is my cost of electricity generation, because I'm not wasting any energy. It's not typically how we look at the efficiency on the system. That's one way to look at it. And I'll explain in a little bit better detail as we move forward. But as far as environmental benefits, I know it's hard to see when you live in a province like BC, especially out here where most of our power comes from hydro. Obviously, in the U.S. where they've got power generated by other fuel sources, including coal. The Oak Ridge National Laboratory report highlights that more than 2/3 of the fuel used to generate power in the U.S. is lost as waste heat. And the report projects that if CHPs were to produce 20% of all U.S. electricity by 2030, and several countries have already achieved that level, CO2 emission reductions would be the equivalent of taking 154 million autos off the road, and more than 5 quadrillion BTUs of fuel would be saved annually, equivalent to nearly half the U.S. household energy consumption. So it does have a significant impact where you don't have hydro generated power. They also have Energy Star. As you know, everybody's familiar with Energy Star, but they have what they call an Emerging Technology Award, and that's to recognize innovative products like CHPs that have the potential to significantly reduce greenhouse gas emissions, and it helps to get over some of the barriers and move the technology forward and hopefully get the cost down where it's going to be more affordable. And there's basically, there's 2 companies that have won that award. One is Marathon Engines with their EcoPower unit, and the other one is actually the Honda Freeway that won that award in 2011, and I think in 2012, I know EcoPower won it again. If we look globally, as a percentage of power generation being produced by combined heat and power in one form or another, you can see that Denmark is the leader in the world with over 50%, probably 54% of their power generation coming from combined heat and power. U.S. is way down here, and Canada's doing a little bit better. But you can see where the technology is going, and we're not just talking micro-CHPs, we're talking CHPs in general, right? So here there was a CHP installed in the LEED Platinum building. This was in the Bronx, and it's called the ELTONA. Now, of course, in New York, their electricity rates are considerably higher than ours. I'm sure they're well over 20 cents a kilowatt hour. Not that we're not going to get there. I think we will. It's just a matter of time. So, case studies, micro-CHP benefits and savings through assistance from the New York State Energy Research and Development Authority. Basically, they're saying it saved $12,936 in building energy costs, avoided 93,000 pounds of CO2 emissions, generated 74,100 kilowatt hours of electricity for common areas, which is 87% of the common area electricity demand, and supplied 574 million BTUs of hot water heating to supplement the space heating. So the original intent when they put these 2 units in there was to take care of the domestic water load and benefit from the electricity that was being generated to offset their common area needs. What they found is that they actually had more than enough capacity for the domestic water, but they also contributed to approximately 25% of the actual heating load for the building. So that's what the mechanical room would look like. These units are, you say, fairly compact, so they're the size of a large boiler, if you like, but not even. Some of them are. We've actually got 2 of these units going into a building in Gastown, probably in the next month or so. where the units have been ordered. We're just waiting to, it's a retrofit. So it's an older building. They're going to rip out the old boilers, put in 2 CHPs for the domestic water load, and use, condensing boiler technology for backup. So the avoided electrical use is $18,000 in this case. The avoided natural gas use was $8,000. Net operating cost savings $12,936. Payback period in that particular situation, based on $95,000 initial cost for the 2 units, is 7.3 years. So there's a lot of variables when you look at this technology, and you have to look at everything. Here's a house. This one's in Langley, and it has 1 CHP unit in it. Now this house is 5,600 square feet. It has an outdoor pool, and it has an outdoor hot tub. It's got radiant floor heating throughout. The house is slab on grade, and it's kind of like a U shape, so there's a lot of slab edge. So it's really an inefficient house to begin with in terms of design and development. For 5,800 square feet. The pool is heated during the summertime, it's turned off during the wintertime. But the hot tub is kept, they keep that going all winter long. All right, so it's got a good annual thermal load. So this is the mechanical room that it's installed in. And here's what's really interesting on this project is that you have an EcoPower unit backed up by 2 geothermal units, 2 water-to-water units. Because it's cheaper to run that EcoPower than it is to run the geothermal units. Yeah, and those are on well water as well, so they've got good entrant water temperature, so they're getting fairly high COPs to begin with. But the CHP, for the most part, keeps up with the load as the peak demand increases. You've got 4 stages of heat pump there that'll come on to back it up. And everything is coupled to this buffer tank. This is a 250-gallon ASME rated tank here that's wrapped. And the way the system is controlled is that we know the CHP, assuming that there's not a lot of load on it, we can get this temperature in this tank up to 167 degrees Fahrenheit. And we know that the geothermal units will never accept that water temperature. You couldn't run them if you wanted to. They would just go off on a high head right away. So the geothermal units don't kick in until this tank temperature drops down to 110 degrees. That's when the geos can kick in and contribute. And then they'll drop out at 120. So we don't have any issues in that respect. So the entire system design is still based on a maximum of 120 degree water. So you've got radiant floor, which is going to be mixed down. And the heat exchangers are large enough for the pool. And the hot tub of that 120 degree water is ample to be able to supply those needs. So it's a very simple control strategy. And as I said earlier, there's 3 sensors in the tank. All that CHP cares about is what's happening in this tank. It doesn't care about anything else in that system. It's not there. It's totally mechanically decoupled from the entire house. So very simple to troubleshoot and very simple operation.
What's the noise factor of this thing?
56 decibels. So it's actually, you can see there's some pumps in here. If I want to hear this unit running, most of the time I got to turn these pumps off. So it's quiet enough. 56 dB is very reasonable. This mechanical room is actually attached to the house, even though we don't have a door going into the house. It's just from the outside door. On the other side of that wall, right behind the CHP, is the hallway and a bedroom. And that thing's running almost 24/7 with no complaints from the homeowner. So if I look at, since the startup on that particular unit, started up March 28th, 2013, and monitored it over a period of about 20 months. And during that time frame, it's produced over 45,000 kilowatt hours of electricity, 119,000 kilowatt hours of thermal energy. So we've got 14,652 hours of runtime during that 20-month period. And it started and stopped 2,283 times. So it'll actually do that automatically whether it needs to or not. It'll stop and do a self-check, checks all its controls, all its safeties, and then it'll start up again. So we expect that to happen. The average power produced per hour since startup is 3.13 kilowatts per hour. The maximum input for the unit is 67,000 BTUs, and the average input, because it will modulate depending on the thermal load. It'll look at that tank temperature. As it approaches the tank temperature, that motor is going to ramp down, and your electricity production will ramp down. Tank temperature drops because you put a load on it, the motor ramps up, starts to produce more power and more heat. So it does modulate. The natural gas that was consumed from March 28th to December 31st, 2014 was 700 gigajoules. And the electricity produced, based on the average, is about 45,909 kilowatt hours. At that time, natural gas was about $8.82 a gigajoule, which meant that the cost for that fuel would have been about $6,174. The avoided electrical cost, we had 45,909 kilowatt hours, where the average cost at that time would have been around 10 cents kilowatt hour. So it's produced as a byproduct, really, $4,591 worth of electricity. So the way we look at CHPs is say, okay, look, I would have had to buy that electricity if I didn't have this CHP. So the savings, if I applied that to the cost of the fuel, I'll end up with a net fuel cost, right? If I look at the amount of thermal energy that I've needed. So the net cost per gigajoule would be reduced down to $2.26 per gigajoule. Net cost per therm, or per 100,000 BTUs, would work out to about 24 cents a therm, as opposed to 93 cents a therm, which is what it was at that time. Then you have to take account into efficiency. The cost per million BTUs of usable energy at 68% efficiency would have been $3.53 for a million BTUs. So Fortis was kind enough to, with the homeowner's permission, provide me with the information on the fuel consumption for that home. And that's where I got those numbers from. I also got permission from the homeowner to access his BC Hydro account so I could see his daily usage as well. And you can see that during this period, you can see where we started at, I said March 28th, where we started to consume some gas. And then, so that's for 2013 and 2014, over a 21-month period. We look at the current cost for natural gas, it's actually gone down. So delivery cost is, $4